the most conventional ways with ultrasound probes, ultratuners, and high pressure homogenizers. I also mentioned that there are other ways, alternative ways, that require lower amounts of energy, but those other alternative methods are not yet that established. So these other three are by far the most used. Another challenge of mini-motion polymerization is this related to the stability, because the stability, the mini-motion has to remain stable at least during the time of polymerization, and eventually longer. If you want to prepare the mini-motion, then store it or transport it up to the time you want to make the polymerization. And here, of course, we have to be careful about coalescence of the droplets of the emulsion that we have discussed a lot last week, and we already know how to minimize it using a surfactant that can provide either a electrostatic or a steric hindrance, or the combination of both. But another aspect has to be taken into account in this case. And that's something that we don't need to care about if we are talking about solid particles, but if we think about liquid droplets or bubbles, then another degradation mechanism must be taken care of. And this other degradation mechanism is the diffusional degradation, also called ripening, in honor of the scientists who studied this degradation mechanism. Ripening is amadurecimento. It's also sometimes translated envelhecimento de oswald. But it's a diffusional degradation mechanism that leads to the destabilization of emulsions and other colloidal systems involving liquid or gaseous phases. But it's quite different from coalescence, because here the particles do not touch each other. Coalescence, they get into contact, touch, and then they may aggregate and coalesce in the case of the droplets. Diffusional degradation doesn't involve the physical contact of the droplet. What happens is that if you have droplets of different sizes, the Laplace pressure of the smaller droplet is higher than of that one, because of the higher curvature here, due to the smaller size. And this higher pressure leads to a higher solubility of the monomer that is inside of the small droplet in the continuous phase than of the monomer that is inside of the bigger droplet. So the diffusional degradation, the monomer that is here in the smaller one, moves to the continuous phase, and from the continuous phase moves to the bigger ones. So in the diffusional degradation mechanism, the bigger droplets increase in size while the smaller ones decrease until they disappear of the system. What is the driving force for diffusional degradation? Is the difference in size. If the monomer droplets are not all exactly the same size, then the diffusional degradation may occur, because of the difference in curvature that is higher in the smaller droplets, that leads to a higher Laplace pressure, that leads to this augmented solubility of the monomer that is in the smaller droplets in the continuous phase compared to the one that is here. So the monomer makes this way, from the small one through the continuous phase to the bigger droplets. They don't touch each other. How can we minimize osmolar ripening, not completely avoid, but diminish it by adding a so-called co-stabilizer. A co-stabilizer is a substance that is added to the dispersed phase. It is in the monomer droplet. Usually it is completely soluble in this phase. You don't see a point, but it's soluble, it's a solution here. It's only a representation for us to see where it is. And so initially, when you prepare your oil phase, you have the monomer, and you have the co-stabilizer, and you have a solution. And then you prepare your mini-emulsion. Then, if you have here a solution, then the composition of this droplet is exactly the same as of this one. You don't have a higher concentration of co-stabilizer here than here. It's exactly the same. Yes. And then what happens? If this droplet is smaller, as indeed it is, then it has a higher Laplace pressure, then the monomer will start to make this way here, through the continuous phase to the bigger one. And as the monomer starts this way, and the co-stabilizer doesn't, because the co-stabilizer, one of its main characteristics in order to be a good co-stabilizer is that it has a very, very low solubility in the continuous phase, much lower than that of the monomer. Then the monomer will make this way, but the co-stabilizer not. So what's the consequence? As soon as the diffusional degradation starts, the composition will not be the same anymore. The concentration of the co-stabilizer here will increase because monomer is leaving, but the co-stabilizer not. And as soon as this monomer reaches the big droplet, the concentration of the co-stabilizer here will decrease further, and the composition will get more and more different. And if we have different compositions, then we have the energy of mixing that will be different here of the mixture. And this energy will counterbalance the difference in the Laplace pressure. That's the idea of the work-acting mechanism of the co-stabilizer, who was studied a lot already in the 1960s by Iguchi and Misra. Not related to mini-motion polymerization, it didn't even exist, this technique at that time, but on studying the stability of emulsions. So, so the idea here is based on the Kelvin's equation. The Kelvin's equation is written in terms of the pressure, but we can write it in terms of the solubility. Here, this is the solubility of the monomer. If it's in a droplet with a radius equal to R here, and this is the solubility on a droplet with infinite radius on a plane surface. Multiplied by this exponential 2 times the interfacial tension between the droplets and the continuous phase, the molar volume of the monomer divided by the radius of the droplet, the same radius here, the big R, the universal constant of gas, temperature. And so what we see here, the lower the radical, the smaller the droplets, the higher will become this solubility. That's the effect behind the osmolar ripening. That's why the bigger droplets increase in size on the cost of the smaller ones. And then, as I mentioned, the idea is to use a co-stabilizer that will not make the same way. That at the beginning, if we have these 2 droplets, droplet 1 and droplet 2, they have exactly the same composition, so the interfacial tension between this droplet 1 and the continuous phase, and between this droplet 2 and the continuous phase, are exactly the same. Gamma 1 is equal to gamma 2, but droplet 1, the diameter is smaller than droplet 2. So, what do we have here at the beginning? We have this difference in interfacial energy based on the difference on the size. Here's in terms of diameter instead of the radius. This will be the driving force for osmotic degradation to occur. Then the monomer will make this moving from the smaller one to the bigger until the smaller one disappears. So, now, if we add a co-stabilizer, as I mentioned at the beginning, the composition is the same. So the interfacial tension of droplet 1 is equal to that of droplet 2, as we see above. And also phi is the volume fraction of monomer in droplet 1 is equal to the volume fraction of monomer in droplet 2. The composition is the same. And in the same way, phi h is the volume fraction of the co-stabilizer. The volume fraction of the co-stabilizer is the same in most particles. Have similar compositions. Again, the only difference at the beginning, droplet 1 is smaller. So at the beginning, we do not have this blue term here. We only have the red one, the interfacial energy due to the difference in the size of the droplets. So diffusional degradation will start to occur in this direction. But as soon as it starts, then the composition will not be the same anymore. This one will have more monomer, a higher volume fraction of monomer than this one, because monomer is making this way and the co-stabilizer not. And then this term will start to grow. It was 0 at the beginning because this was equal to this, then it was 0. But as soon as diffusion degradation starts, this won't be the same anymore, and this blue term will not be 0 anymore. And this term goes in the opposite direction as this one. And as soon as this term has the same magnitude as this one, it will counterbalance, and then we will say that a kind of a steady state, pseudo-steady state, is reached where the droplets are critically stabilized against osmotic brightening. So the co-stabilizer doesn't avoid diffusional degradation, but it makes it stop at a certain point. An important thing, we want it to stop in terms of colloidal stability. We want it to stop as fast as possible. So the higher M, the better. The sooner it will stop, the bigger will be this term compared to this one, and the sooner the fusion degradation will stop. And who is M? M is the ratio between the molar masses of the monomer and the co-stabilizer. And that's an important point because I already mentioned that an important characteristic of the co-stabilizer is being insoluble or as little soluble as possible in the continuous phase. And then if we are talking about many-motion polymerization, a good idea would be a polymer that is not soluble in water. But, okay, in terms of solubility, it would be good. But it would not be good if we look at M, because if the co-stabilizer is a polymer, there is molar mass here, it's much higher than that of the monomer, and M will be small. So we will need a very high difference in composition until this term here gets equal to this one. So a good co-stabilizer must not be soluble in the continuous phase, but must be a small molecule, a low molar mass molecule, in order to have a bigger value of M here. And then here you can see the chemical potential of both particles, of the small droplets that have a much higher chemical potential due to the interfacial energy than the big droplets. And as diffusion or degradation occurs, they will approach each other and get the same. Well, here they are up from here, they are pretty stabilized. In terms of diameter, those are the initial diameters of the droplets. Droplet 2 slightly bigger than droplet 1, but as diffusion or degradation starts, this difference will increase until they are critically stabilized. This I already mentioned. With what the effect of the post-stabilizer time. It has to not to be soluble in the continuous phase, but it has to be a low molar mass. And this can be observed here in this graphic. Here we have at this point the ratio between the diameters of droplet 1, the ratio between the diameter that is reached by the droplet at the end and the initial diameter of droplet 1. So if no diffusion or degradation would occur, this ratio would be equal to 1. It would not change. If this ratio gets below 1, this indicates that diffusion or degradation is occurring. And the lower this ratio becomes, the more intense is the diffusion or degradation. And the smaller the small particle is getting. And here, on the x-axis, what we have is the ratio between the initial diameters of both particles, the big one and the small one. If we are here in 1, they are exactly the same size. If they are the same size, no diffusion or degradation will occur. But if droplet 2 is slightly bigger than droplet 1, degradation already starts. That's what we see here with the high slope at the beginning of this graphic, already when the difference of the size is relatively small. Here we are at 2, here we are at 4, so it means that here we are at 1, here 1.5. So the highest degradation already occurs here with a difference from 1 to 1.5 here already, with the decrease of the size of the smaller droplet. And also what we observe is the effect of the M I mentioned, the ratio between the molar masses of the monomer and the co-stabilizer. If this M, the value of M is 0.5, then we will have the upper curve. Degradation occurs, and then it will stabilize as soon as the size of the smaller droplets reaches about slightly above 60% of its original size. It decreased in size, but up to 60% of its original value. If we decrease the value of M from 0.5 to 0.3, then we move to this curve here, and it will only stabilize here around 55% of its original value. If we make M0, it stabilizes with a very high molar mass, as for instance polymer, then we'll get here. The droplets will decrease much more in size, and the ratio starts at 1 and instantly drops to 0.4, and already an infinite difference in size between the big droplet and the small droplet. So here we can clearly see the effect of the molar mass of the co-stabilizer. So So the higher the molar mass of the co-stabilizer, the lower the droplet stability. That's what we see here. And whatever droplet size distribution, a low droplet stability is predicted when using polymer as co-stabilizer. Polymer is a poor co-stabilizer. That's what we see here. Here, as soon as we move from one, as soon as the size is not exactly the same anymore between those droplets, you have a strong diffusional degradation. And if we use a good co-stabilizer, the broader the initial droplet size distribution, the more also ripening we will have. Because it's the difference in size is the driving force of also ripening. In a conventional emulsion polymerization, we don't care really too much about Oswald ripening. And why is that? Because in conventional emulsion polymerization, at the beginning of the reaction, we have the monomer droplets, but they are relatively big. And emulsion polymerization, during the whole reaction, we have the stirring. And if the droplets, for any reason, start to grow, if they coalesce, or if there is a fusion degradation, they will be broken again due to the stirring. Then it's not really a problem in terms of the big monomer droplets of an emulsion polymerization. In the same way, it's not a problem in a suspension polymerization. The polymer particles that are formed during the emulsion polymerization, okay, they are very small. They will not be broken here anymore. But the polymer particles, as the name tells, contain polymer and contain monomer. And they contain lots of polymer. So these lots of polymer, though being a bad co-stabilizer, will minimize Oswald ripening in this case of the polymer particles, because the particles are formed mainly by polymer. In the case of the mini-emulsion polymerization, then it's quicksolved, because at the beginning we have a liquid mini-emulsion. The droplet size is far too big, so stirring doesn't decrease the size of the droplet. It can eventually increase because it will increase the amount of contact between the droplets and the energy that droplets carry when they get into contact, but they will not be able to break the droplets. And then for mid-emulsion polymerization, diffusional degradation is an important issue. And that's why in mid-emulsion polymerization we add a co-stabilizer. Here we have the effect of the amount of a co-stabilizer, of a good co-stabilizer, a low molecular weight co-stabilizer. As for instance, one of the most used is hexadecane. And here we can see the decrease. If we use, for instance, volume fractions of 0.005, that would be not enough. We observe a strong decrease in the size of this smaller particle. The ratio starts at 1, and already with a small difference in size, and up here. If we increase the amount, that's the volume fraction of the co-stabilizer in the dispersed phase, not in the whole formulation, but in the dispersed phase. If we increase it, we move upwards. And what we observe here in those three curves above, we have Oswald ripening, a slide, but it doesn't decrease too much the size of the smaller droplets. At the end, it has around between 90 and 96% of its original size. So typically, for a good co-stabilizer, said that about 4 weight percent or volume percent of a good co-stabilizer are enough in order to protect against Oswald ripening. Here are some comparisons of different co-stabilizers. So, the lower the water solubility, the better is the co-stabilizer, because it has to remain in the original droplets. So, hexadecane, as I mentioned, is one of the most used co-stabilizers. At the first studies involving mini-motion polymerization performed at the University of Lehigh, they used cetyl alcohol as a co-stabilizer. It's not a good co-stabilizer. It works, but much worse than hexadecane. So at the first studies in 1970s, 80s, cetyl alcohol was used a lot in mini-motion polymerization. Nowadays, it's almost not used anymore simply because it's not a good co-stabilizer. Its solubility of this in the water phase is much too high for it to be a good co-stabilizer. And here in the middle are two other examples. Real methacrylate or real methacrylate. Those are methacrylates are monomer with a double bond that can be polymerized by a free radical mechanism. This is 12 monomers. This is 12 carbon atoms in the chain. Here 20. So they are quite hydrophobic and consequently have a low solubility in water. The methacrylate will enhance somewhat the polarity of this monomer, but this long chain turns them more hydrophobic. So they can be used as well, and they are interesting to be used in many motion polymerization, because the co-stabilizer at the end of the polymerization will remain inside of the polymer particle, will affect the properties of the material. So in this case, it's interesting to use a monomer, a hydrophobic monomer, as co-stabilizer, because at the end it will be co-polymerized in the polymer particle, forming the polymer, and not be a low molecular weight molecule that is present in the particle. For some applications, it is nice to have low molecular weight molecules inside of the particle. Indeed, it is done. We will talk about it next week. For instance, to encapsulate oils and fragrances, as I mentioned, it can be a very nice way, and these oils and fragrances can be the co-stabilizer. Then we want to have it there. But for other applications, we don't want it. And then to have a monomer playing the role of the co-stabilizer is very interesting. That's why those two are here also. They are not so good as hexadecane, but much better than cetyl alcohol and can indeed be used. Another point, in order to affect having another type of molecule inside of the polymer particles at the end of the reaction, would be to use as co-stabilizer the polymer, preformed polymer. But we have seen a polymer is not a good co-stabilizer because of its high molar mass. It can be used, but it's much worse than hexadecane. This is an example of a mini motion prepared with the monomer methyl methacrylate, and then one of them was prepared with hexadecane, and the mini motion without polymerization remained stable for a time interval between 3 weeks to 3 months. The liquid mini motion, the submicrometric monomer droplets dispersed in the continuous active phase by adding a small amount of hexadecane to the methyl methacrylate droplets. If instead of using hexadecane, the polymethyl methacrylate would be used, this time, instead of being 3 weeks to 3 months, would be 6 hours. But during 6 hours, the mini motion would remain stable. So if we prepare the mini motion and perform a reaction that takes less than 6 hours immediately after preparing the mini motion, then eventually PMMA could be used as co-stabilizer, even not being a good co-stabilizer. It's much worse, but it could be used. If we have to prepare the mini motion and then transfer it transport it or store it and only do afterwards polymerization, then it would not be a good idea. And here about the amount of a good co-stabilizer as hexadecane. HDs for hexadecane. 3 to 4% usually are mentioned to be enough in order to provide a good stabilization against post-storm wrapping. Well, the other point of the mini-motion polymerization is that the whole idea is to polymerize the monomer droplets. So, in this case, the nucleation mechanism of the polymer particles is a droplet nucleation, and not the micellar nucleation that we have seen in conventional emulsion polymerization, and not the homogeneous nucleation. Yes. So, what do we need to guarantee or to favor droplet nucleation? First of all, we don't want to have the presence of micelles, because if we have micelles, and if we have a free radical polymerization, especially if we use an initiator that is soluble in water, then we will have micellar nucleation, and parts of the particle will be formed by micellar nucleation, and then we will have an emulsion polymerization, and not a mini-motion. To have a mini-motion polymerization, most of the particles must be formed by droplet nucleation. So we don't want to have micelles. But here I always like to remember, this doesn't mean necessarily that the concentration of surfactant used is below the critical micellar concentration. Because if we have water and surfactant, then we will have the formation of micelles if we have a concentration of surfactant below the micellar concentration. But below that, above the critical micellar concentration. But if we have monomer droplets, part of the surfactant moves to the interface between the monomer droplets and the aqueous phase. And the higher this interfacial area, the more surfactant will move to this interface. And so what we have to guarantee in the mini-motion polymerization is that the concentration of surfactant that is soluble in the continuous phase is not above the critical micellar concentration. But a high amount will be on the surface of the particles. How do we measure the critical micellar concentration? One of the simplest ways to measure it, and that works for any kind of surfactant, no matter if it's ionic or non-ionic, is to measure the effect of surfactant concentration on surface tension. To measure surface tension is a function of surfactant concentration. If you have water, you measure the surface tension of pure water. It will be here. You add a certain amount of a given surfactant. If it's a surfactant, it will decrease the surface tension of this solution. You will have here. If we add more surfactant, increase the concentration of surfactant, it will decrease further and further and further and further and further until it stabilizes at a certain point. And then, if we want to know the critical micellar concentration, what we make here is at this point making it like this and like this, the tangent, and then here this intersection is the critical micellar concentration of the surfactant. This is if we have only the surfactant in water. Now we have an emulsion. we don't have only water, but we have water with droplets of a monomer or of another oil. What do we have here? At the beginning, without any surfactant, we will measure here the surface tension of pure water of the continuous phase. We will be here. But then if we add some surfactant, the surfactant will be here the air-water interface, will be here the continuous phase, but will be part of it be at the interface between the droplets and the continuous phase. Then the next point, instead of being here, will be here above at a certain point. And here, and here, and here. And then, up to here, this will be the new critical micellar concentration. But the critical micellar concentration is not that one, it's this one here. This amount here is the amount that is on the surface of these droplets here. So, and if we, instead of preparing this, we would prepare a mini-emulsion, and the monomer droplets are much smaller and numerous, and consequently the total surface area is much bigger, then instead of having this, we would have something like this. And we would be here. And this amount here will be on the surface of these droplets. So, in a mini-emulsion, we can work, if we have this droplet size, we can add an amount of surfactant up to here, and we will not have micelles. We are much above the critical micellar concentration, but we will not have micelles because this excess of surfactant is at the interface between the droplets and the continuous phase. That's why we often work above the critical micellar concentration, but still don't have micelles. We have to be careful not to be here, because if we are here, we might have micellar nucleation. But if we are here, we are in a safe point. And often, working below this is not a good idea, because then we wouldn't have enough surfactant to cover well the droplets. Usually, we say that the surface area, we need a coverage of about 40 to 50% of the area by the surfactant in order to have a good colloidal stability.
And how can we know the micellar critical?
How can we know what? Excuse me?
Critical micellar concentration.
To know the micellar concentration, we can make this type of measurements of the surfactant
you need
in water. Yeah.
Okay.
But then, if you know another parameter that can be measured by surface measurements as well, which is usually called AS. AS is the area covered by either mole of surfactant or molecule of surfactant. You have to pay attention if the base is mole or molecular. Yeah. If you know this parameter, then you can calculate what is the expected total surface area of your droplets and how much surfactant you will need to cover the droplets. This parameter, it will depend mainly on the surfactant type and on the material of your droplet. For monomer A, it's one value, for monomer B, it's another, for the polymer, a different, and so on. And it can be determined based on surface tension measurements in the presence of the droplets. Can be done. So, if we have, we'll perform a free radical polymerization and use an a monomer that is soluble in the water phase or in the continuous phase. In terms of droplet nucleation, using an initiator that is soluble in the dispersed phase has advantages because it will minimize an occurrence of homogeneous nucleation. If the radicals are formed in the continuous phase, then they might precipitate, forming new particles before they grow and enter a monomer droplet. Yeah. And we don't want this to happen in a mini-motion polymerization. And another point that helps a lot to favor a droplet nucleation is to have a high number of droplets and then also of particles, to have a high total surface area. If the radicals are formed in the continuous phase, if we have a high surface area for these radicals to quickly enter, then we will minimize the possibility of those radicals to grow into reaching the size required for homogeneous nucleation to occur. And so the higher number of particles, the higher total surface area here, the better to avoid other nucleation mechanisms besides droplet nucleation that is the wanted mechanism in this case. So, in many motion polymerization, we can choose between using, if it's a free radical polymerization, we can choose between hydrosoluble and organosoluble initiators. If it's soluble in water, the radicals will be formed in the aqueous phase, just the same way as you have seen in emulsion polymerization. The difference here is that we want those radicals to grow here in water and then enter the monomer droplets. And in this case, in the mini-motion polymerization, since the monomer droplets are much, much smaller than in the case of the motion polymerization, the total surface area of the monomer droplets is much higher. It will be a high enough area for those radicals to enter quickly and to nucleate the droplet. Once such a radical enters a monomer, this radical is so reactive, it will start reacting with the monomer here, and then this droplet is nucleated by the droplet nucleation mechanism. And the more monomer droplets we have, the faster this will happen. And by mini-motion polymerization, this is perfectly possible. Differently from what happens in, for instance, a suspension polymerization. A suspension polymerization, we also have the droplet polymerization, but the droplets are very big, so their total surface area is orders of magnitude smaller, and then it will take a long, long time for those radicals formed in water to reach a particle and enter and droplet nucleation to occur. So in suspension polymerization, all organosoluble initiators are used. But in mini-motion polymerization, we can choose. If we use our organosoluble, then the initiator is mainly inside of the monomer droplet. The radicals are formed here inside, and the polymerization can proceed. Here it explains more or less what I have already explained now, the droplet nucleation mechanism when a water-soluble initiator is used. Most initiators decompose, forming two radicals, and then they can propagate. If they are not hydrophobic enough to enter directly the monomer droplet, they will propagate in the aqueous phase until they enter the monomer droplet, where polymerization can proceed by the conventional free radical reactions: propagation, termination, and then eventually transfer. Here, transfer to monomer is important because if transfer to monomer occurs, the new radical formed, the monomeric radical, this can eventually exit the monomer droplet. The same way as you have seen in motion polymerization. Since it's a very small species, it has a certain solubility in the continuous phase. So here, it's quite similar to motion polymerization. The difference is that they do not enter a micelle or a preformed polymer particle, but they enter the monomer droplets. we don't want to have the presence of micelles. Otherwise, those radicals formed in the aqueous phase will also enter micelles, and we will have miscellaneous nucleation, what we do not want. And also, we do not want homogeneous nucleation to occur. Homogeneous nucleation, as you have already studied with Christian in conventional emulsion polymerization, the radical grows in the aqueous phase. If it doesn't find an interface in which it could enter, it will continue to grow until it is not soluble anymore, and it precipitates, forming a particle by homogeneous nucleation. Just as I have already studied. In many emulsion polymerization, we don't want this to happen also. And how can we avoid this? If we use an initiator that is soluble in water, one way to minimizing this is to have a high enough surface area for these radicals to enter, so that they are not able to reach this critical size in the continuous phase. So here, the higher the number of particles, the higher the solid constant, the better. So, to favor droplet nucleation, we don't want the presence of micelles in order to avoid miscellaneous nucleation, and we want a high number of particles or droplets, a high total surface area, in order to minimize homogeneous nucleation. Homogeneous nucleation will occur if the radical starts to grow and doesn't find another interface to enter. If it finds it, it will enter, and no homogeneous nucleation will occur. Well, the other possibility is to use an initiator that is soluble in the organic phase. This also works in a mini emulsion polymerization. It has the advantage because in terms of minimizing other nucleation mechanisms, because radicals are already formed inside of the droplets, that in terms of maximizing droplet nucleation, the use of organosoluble initiator is very favorable. This will be a great advantage. In terms of practical issues, organosoluble initiators are not so practical to be used. It can be used, but it's not so practical. And why? Because if the initiator is soluble in the continuous phase, then we can prepare the mini emulsion, put the mini emulsion into the reactor, heat it to the reaction temperature, and when we want the reactor to start, then we add a small amount of water containing the initiator. As it is soluble in the continuous phase, we can add it only at this point. So we can set exactly the point at which we start the polymerization. If we use organosoluble initiator, then it has to be there in the organic phase right from the start. When we prepare the mini emulsion, the initiator is already inside of the monomer droplets. So we have to be careful during the preparation of the mini emulsion, because we have seen here when we add the energy, the undesired collateral effect is that part of the energy is lost as heat, so the temperature increases. That's why I forgot to mention that usually the mini emulsification is performed in an ice bath or another bath using a recirculation bath in order to avoid the temperature to increase too much, especially if the initiator is already there, because otherwise the initiator could start to decompose, start forming the radicals, and polymerization could start prematurely. And then, for instance, you take the mini emulsion to the reactor, the initiator is already there. The heating time, the reaction will already start to occur. You will not be able to perform the reaction under completely isothermal condition. you will start to heat the reaction medium. The initiator is already there. The reaction will start slower due to the lower temperature at the beginning, but it will already start. Whereas if you use the water-soluble initiator, you can already heat the system, and only afterwards, when you want to start the reaction, you add the initiator. So there are advantages and disadvantages of each type of initiator in the case of medium motion polymerization. In terms of favoring droplet mutation, oil-soluble initiators are very good. But in terms of practical aspects of the polymerization, aqueous phase initiators have advantages. So both types of initiators can be used and effectively are used. The point is, if we choose to use a water-soluble initiator, we have to be more careful to avoid other mediation mechanisms. Another point that is important when you work with organosoluble initiators is that, okay, the initiator is inside of the droplet. The initiator decomposes and forms two radicals. Free radicals, are very reactive species, as we already know. And if they are very close to each other, and they necessarily are, because this droplet is very small, 200 nanometers, then the probability of recombination of those two radicals is very high. And if they recombine, they may recombine not forming the original initiator anymore, but forming a different configuration, a different molecule that won't decompose anymore. So what happens is that a high amount of the initiator could be lost here in this recombination reactions without starting effectively a new polymer chain. So the efficiency of the oil-soluble initiator is lower in this case. Also compared to the same initiator when it's used in bulk or in solution. Because in bulk, the initiator decomposes and they can move apart. They are free to move. Here not. They are confined inside of this tiny monomer droplet, so they are necessarily close to each other. So there are several theories, and the most accepted theories of today is describing that it's required to have the initiator decompose, forms two radicals, and when one of these radicals exits the monomer droplet, being a small piece you can exit, then you will have a single radical inside of the droplet, and this single radical then will start the polymerization inside of the droplet. So the efficiency of the radical initiator is much lower when oil-soluble initiators are used in medium motion due to this small place to which they are confined. This doesn't, we still can use organosoluble initiators. It works, but the reaction becomes slower than expected, or we would need to add higher amounts of initiator. Anyway, in case of medium motion polymerization, we have the same compartmentalization effects of the radicals that you already studied for conventional motion polymerization. If it's a free radical polymerization, then due to the very small size of the monomer droplets, polymer particles, the radicals are distributed between a very, very high number of droplets and particles. Consequently, the concentration of radicals per droplet particle is very, very low, often much below 1. And if there is only one radical here, this radical will not terminate until a second radical is formed here. So, if it terminates less, then at the end, what do we have? Higher radical concentrations. Higher radical concentrations means higher reaction rates, faster reactions. And in addition, if they terminate less, the radicals have longer times to grow. Consequently, we can reach higher molar masses. So the same effect of radical compartmentalization that you studied for motion polymerization also applies for free radical polymerizations performed in medium motion. can be seen here. Here are simulation studies, but here we had also some experimental results. They're not shown in this graphic, but it's also experimentally proven. Here are mini-motion polymerization results of styrene mini-motion using a hydrosol initiator, potassium persulfate. The formulation is all the same. The difference is only in the size of the monomer droplets. 130 nanometers, 150, 170 nanometers. And we see the difference isn't that much. 130 to 250. Here's 7, I think I said it wrong. These one are the biggest particles, 170, 150, 130. And the smaller the particles or the droplets, actually at the beginning, the faster is the reaction. Why? Because if they are smaller, if we have the same amount of monomer, then we have more monomer droplets. We have a more intense compartmentalization effect, and the reaction becomes faster, as we see here. So those droplets are smaller than these, and these are smaller than these. And the same type of behavior may be observed here using an oil-soluble initiator with different diameters, 100 nanometer, 200, 300, and so on. The bigger the droplets, the slower becomes the reaction. With the same amount of initiator, same temperature, everything the same, the only difference is the droplet size at the beginning of the reaction, and consequently the particle size, then, since we're talking about a mini-motion polymerization. And here, this last curve here is of a bulk polymerization. And we can study up from which size we don't have the effect of radical compartmentalization anymore, which happens here for this formulation at around 600 nanometers. The behavior is more or less the same as of a bulk polymerization. So for both types of initiators, we have the effect of radical compartmentalization. And now to finish, talk a little bit about what I mentioned based on Larissa's question. When do we apply mini-motion polymerization? As I mentioned, the particle size is the same range as a conventional motion polymerization. The term mini refers only to the monomers droplets, not to the polymer particles. We may have polymer particles prepared by mini-motion polymerization with an average size around 100 or 80, or it could be 300, and in the same way with the motion polymerization. So in terms of particle size, they are exactly the same. But emulsion polymerization is an older technique, very well established. The process to produce styrene butadiene rubber via emulsion polymerization to produce the rubber for tires is a process that was established in the 1950s, and the same process is used up to today mainly. So it's very, very well established. What has improved a lot is the monitoring of these types of reactions. But the process is mainly the same and works pretty well. And if we talk about industrial applications, they won't change from emulsion to mini-motion just for nothing. Emulsion is well established, requires one step less. You don't need to prepare the mini-motion, and requires less equipment, less time, less energy. So when is it interesting to work with mini-motion polymerization? When conventional emulsion polymerization fails. And one important aspect here is emulsion polymerization works very well for free radical polymerizations. Chain polymerization via a free radical polymerization mechanism. But emulsion polymerization may not be used for step growth polymerization. And why? Because if we have both monomers in the droplets of the emulsion, if it's a step-cross polymerization between the functional groups of the monomers, they will start to react. The reaction will proceed, but the reaction will occur inside of the monomer droplets. And if it's and then it will not be an emulsion polymerization. It will be a suspension polymerization. At the end of the polymerization, step-cross polymerization, we will have polymer particles that are more or less that of the size of the initial monomer droplets. It will be a suspension polymerization via step-cross polymerization mechanism, but not an emulsion. If you want to prepare directly in situ supermicrometric polymer particles by a step-cross polymerization mechanism, emulsion polymerization fails. And step-cross polymerization is very important. Polyurethanes are prepared by step-cross polymerization. Lots of polyesters like nylon, PET, and so on are formed by step-cross polymerization. And it simply can't be done via conventional emulsion polymerization. Then for these types of reaction with this step-cross polymerization mechanism, mini-emulsion polymerization is very interesting because it can't be done in emulsion. And there are other examples of other mechanisms. It can be chain growth polymerization mechanisms. Ionic polymerization are very difficult to be performed in conventional emulsion, but can be more easily performed in mini-emulsion. In the same way as several catalytic polymerization using metallocene or xylanate catalysts, organometallic catalysts, also with enzymatic catalysts. It's much easier, it's very difficult to perform it in conventional emulsion polymerization, but in mini-emulsion polymerization it can be done. Controlled free radical polymerization, which is a type of free radical polymerization, but with a control agent that controls the architecture of the chain formed. It can be done sometimes in emulsion polymerization, but it's more difficult because this control agent usually is less soluble in the continuous phase, so it is difficult to make the way from the droplets to the particles and so on. And so that's why these polymerizations are much easily performed in mini-emulsion than in emulsion, as well as other polymerization mechanisms like thiolene polymerization and so on that could be very interesting to synthesize polymers based on renewable monomers, and also to synthesize polymers including functional groups, ester bonds in the main polymer chains that can be more easily degraded. These polymerizations are relatively easily performed in mini-emulsion and not in emulsion, because they would have exactly the same thing as a step-cross polymerization. It would be a suspension polymerization and an emulsion polymerization. Other aspects that can be explored in mini-emulsion polymerization is in relation to the reactor type. Emulsion polymerization are limited to stearate, or mostly limited to stearate tank reaction. And why? We need this. Put it away. We need the steering in order to keep the monomer dispersed as droplets. If we start the steering, the monomer droplets of the emulsion will start to coalesce and move upwards on the reactor, and then the interfacial tension between the monomer and the water will be very low, and the reaction would become very, very slow. It would not happen. So we need the steering during an emulsion polymerization. And that's why we cannot perform an emulsion polymerization in an ideal tubular reactor, in a group flow reactor, because along the reactor, the emulsion would destabilize and the reaction would not occur. Mini-emulsion polymerization, if the mini-emulsion is colloidally stable, can be performed in tubular reactors without problems. And tubular reactors have advantages, especially if we talk about polymerization, because polymerization reactions are very exothermic reactions. The compartmentalization effect on consequence is higher reaction rate, which is very good in terms of productivity, but in terms of security of the process, it's not necessarily so good, because higher reactor rates also imply in higher heat generation rates, and we need to have the capacity to remove all those heat. Otherwise, its reaction temperature would increase, and if the reaction temperature increases, the reaction rate increases further, and so on. And in the past, this already led to explosion, to industrial scale polymerization plants. Nowadays, it's not less frequent because we have much better monitoring and control systems. But anyway, in polymerization processes, the heat removal capacity is an important issue. And one way to increase the heat removal is by increasing the heat removal area. And we can do this by the aspect ratio. Tubular reactor, we have a much higher ratio between the surface area of the reactor and the volume compared to a stereotank reactor. And so that's, in certain cases, it's really advantageous to move to this type of reactor. And in mini motion polarization, that can be easily done. Another point that could be interesting for mini motion polarization is if we want to incorporate hydrophobic monomers. In a conventional emulsion polymerization, if we have a monomer that is completely insoluble in water, we cannot polymerize it via emulsion polymerization because it would remain in the droplet. It would not move to the polymer particle, to the micelle, so the polymerization would not occur. Or even if it's a co-monomer, one monomer would polymerize, but the hydrophobic one would remain in the droplet. In the mini motion polymerization, that's not the problem, since the polymerization starts in the droplet and as it is inflated, it's turned into the polymer particle. So it's a very nice way for the incorporation of hydrophobic monomers. And the use of hydrophobic monomers is very important from an application point of view if we want to have more hydrophobic surfaces. That's important for self-cleaning paints. This is important for textiles, paints for cars, for whatever the surfaces for cell phones. Here we want it to be hydrophobic, but also oleophobic, and so on. So for this is also very interesting mini motion polymerization, and also for the preparation of hybrid particles containing other types of materials, and the encapsulation of oils, drugs, fragrances, other particles, inorganic particles, silver nanoparticles, gold nanoparticles, titanium dioxide, whatsoever, whatever we want to think about encapsulation. It can, some of them can be done via conventional emulsion polymerization, but it's much more difficult. In mini emulsion polymerization, it's a more direct way. If we have what we want to encapsulate inside of the same droplet, and we polymerize this droplet in a way that the substance that we want to encapsulate is not expelled during polymerization, then we may have much better success in a simpler way using mini emulsion polymerization than emulsion polymerization. So for the encapsulation of different material substances, mini emulsion polymerization is also a very, very nice technique. So for all those situations in which emulsion polymerization cannot be applied or is difficult, very tricky to be applied, then mini emulsion can be interesting. Otherwise, if it's something that we can easily do in emulsion polymerization, then go on doing it as emulsion polymerization, not move to mini emulsion, because at least at an industrial scale it would not be interesting. Next week we'll still talk about mini emulsion polymerization. We'll talk about several examples of different kinds of materials that can be prepared by this technique. And next week, then we'll also make some questions about many motion polymerization. Anyway, if you have that questions now, then next week we're going to have something like this that we had last week. But if you have doubts, questions, comments, suggestions, and if you have some experience related to the topic and want to share it with us, feel free any moment to interrupt me.
Professor, evaluation of these papers will be only oral?
Only oral, yes. Only the last one, then that will be made individually without consulting during class. This you have to hand in.
So
the other ones is
next
only
week we're going to have something like this.
Exactly. Mm-hmm. If for any instance any one of you isn't able to come on one of these days when we have this, then you can hand it in afterwards for you to have a yes, your marks for this as well. But if you are here, then you don't need to hand it in. Oh, thank you. I will look if it's possible next week then to be at auditorium.